All right, hi everyone. In this video, we are going to go into chapter 25 and start with section 25.2, which is called the indefinite integral, and introduce something different. So far, all semester, we have been taking derivative, applications with derivatives, derivative. Now we're not. We're going to do something. We're going to learn about something called an integral. An integral is the opposite of a derivative. So in the past in math classes, first you learn how to multiply things, then you learn how to factor them apart. You multiply and put them together, you factor, you break them apart. An integral that we'll see in this section is the opposite of a derivative. What's kind of cool in the history of math, when calculus was first being developed, there was a guy named Newton and there was a guy named Leibniz, and one of them was developing differential calculus. Newton was. That's derivative calculus. And the other one, Leibniz, he was developing integral calculus, and they were almost doing it at the same time, and they both published books at pretty similar times. And so they kind of come at calculus from opposite ends and meet in the middle, and it's kind of cool. All right. So kind of to introduce this topic, I'm going to write down a couple of different functions. The first one is x cubed. The second one is x cubed plus 4. The second one is x cubed minus 7. The next one is x cubed plus 4 pi. Okay. And the question is, what do all of those functions have in common in terms of derivatives that we just did, that we're finishing up? If I take the derivative of any of those four functions, the derivative is 3x squared of all four. So taking the derivative of those four functions, it leaves off, we lose the constant that's after the x cubed term, and they all have the same derivative. All right, so that's important to know going into this. Okay, so what is integration? Well, integration is saying, well, let's say that I start out with, and I'm going to use a capital F that I'll talk about a little bit more in the next slide. Let's say I start out with capital F of x equals 3x squared. Okay, that's my function that I'm starting with. I want to know, what is little f of x? What is lowercase f of x? What is that equal to? Let me throw a little question mark there. What is that equal to, so that little f prime of x is equal to capital F of x? Okay, what is the function whose derivative is 3x squared? Well, whose derivative is 3x squared. Well, what I just did at the top, I mean, that's kind of the answer. The answer is that little f of x is equal to x cubed. Oops, x cubed. But which x cubed is it? Is it this one? Is it this one? Is it that one? Or is it that one? Well, we don't really know without a little bit more information. So what we do is we say, okay, that is equal to x cubed, but we're going to add on a plus c, where c is some constant. I don't know what it is without more information about little f of x. It could be a 4, it could be a minus 7, it could be a 4 pi, it could potentially be 0. Okay, so that's kind of what's going on here. Now, on this next slide, we'll get into notation. How do we write these integrals? Well, so there's lots of symbols and signs here that I'm going to introduce. So listen to it twice if you need to catch all of it. Right. So what I'm going to write is a squiggly looking long s. That's the technical term. And then my function f of x, and then dx, and then I'm going to write capital F of x plus c. Okay, so what the heck is all that? Well, this guy right here, that little long looking s, that's an integral sign. INTEGRAL. It's from the term integration. That's the thing that we're doing. Okay. This f of x right there, he's called the integrand. Oops, IN. Okay. That's the function that we are integrating. That we're taking the integral of, and then this whole thing is called an indefinite integral. Okay, it's called an indefinite integral. Oh, and also, while I'm at it, that dx there, that is just the variable of integration. Okay, it basically just represents what we are taking the integral in terms of, right? With derivatives, we take the derivative with respect to x, so we write dy over dx. This dx represents the variable that we're integrating with respect to. In Calculus 3, we take integrals with respect to all kinds of different variables within integrals, okay? Or integrals with respect to all kinds of variables. Okay, so now more terms and notation to throw at you. On the right-hand side of the equal sign here, that f of x, capital F of x plus c, is called the antiderivative. It's the antiderivative, all right? And then the c that I mentioned on the previous slide, that is the constant of integration. Okay, could be a 7, could be a 3, could be a 15, but it's a constant. Okay, and then capital F prime of x, by the way, is equal to little f of x, which is, again, what I have had in the last slide. All right, so there's a lot of notation. Go back, listen to it again. Remember, be able to recognize what each word means, because I'm going to use all of these words moving forward. Okay. All right, as a little example here, just a brief example, if I am taking the integral of 5x to the fourth with respect to x, I'm asking what is the function whose derivative is 5x to the fourth. Pause and think about it for a minute if you want to. But the answer is x to the fifth plus c, plus our constant of integration. And how do I know that's the answer? Because I'm really good at derivatives by this point in the semester. The derivative of x to the fifth, 5x to the fourth. Okay, so that's how that one works. Okay, so the integral of 5x to the fourth with respect to x is x to the fifth plus c. All right, now we get to some formulas, some things to commit to memory to make integration a little bit more straightforward. First thing, if I'm integrating c dx, the integral of a constant. The integral of a constant. Well, what I've got to think is, what do I take the derivative of and produce a constant? Well, the answer is that constant times x. Right? If I take the derivative of 4x, the answer is 4. If I take the derivative of 3x, the answer is 3. So the derivative of a constant, or the derivative of a constant times x, is the constant. So when we integrate a constant, we get c times x. But then we've got to tack on our plus, capital C, the constant of integration. All right, so there's our first formula. Second formula, if I am integrating du plus dv. All right, so what the heck does that mean? If I am integrating a sum of two terms, basically, all right, that is u plus v plus, why did I write a d? Plus c. All right, what does that mean? If I'm integrating a sum of terms, then I integrate each term individually. Right? The integral of du is u, the integral of dv is v, the integral of dx is x. Okay, so just basically it means take the integral of each term individually. All right, and now here's the big one. This next one's a big one. The integral of x to a power dx. Okay, so how do I integrate x to a power? We just did one example on the previous slide. Integral of 5x to the fourth was x to the fifth, right? When you take a derivative, the exponent gets smaller. So hopefully it stands to reason that when I take an integral, an antiderivative, the exponent gets bigger, right? By 1, because with derivatives, it got smaller by 1. So the integral of x to the n is x to the n plus 1. But instead of that exponent coming down in front, as it does with derivatives, it goes down into the denominator, divided by n plus 1. And then we tack on our plus c. So that's our power rule for antiderivatives. Power rule. This guy is our sum rule. Not really rules, they're just how antiderivatives work. And this guy is our constant rule. Again, not really rules per se, they're just the way that they work. Okay. All right, so there's our three things, and I would say commit them to memory. You're going to be using them a lot, just like we did with our different rules for derivatives. All right, on this slide, we'll go through a couple of examples. The integral of 6x dx. All right, so we use that power rule. 6x, exponent's 1, so now it's 1 plus 1 in the exponent, divided by 1 plus 1. Am I going to write 1 plus 1 down every time? No, of course not. I'm just adding emphasis here. Plus c. You're going to forget that plus c. Don't forget that plus c. So that equals, simplifying a little bit, 6x squared over 2. And that equals 3. Oop, I lost my plus c. See, I did it myself. Plus c. And that equals 3x squared plus c. Okay, and then check that with a derivative. Derivative of 3x squared, hey, 6x. I got it right. The second problem, the integral, now I've got a sum of terms, so I'm going to take the integral of each term individually. So 5x to the fourth, 3 plus 1 is 4, over 4, minus 6x to the third, over 3. 2 plus 1 is 3, over 3, plus 1. That looks a little bit weird. The antiderivative of 1, it's a constant, so a constant times x. 1x, you don't have to write the 1. I'll drop it off when I rewrite this, simplified, plus c. All right, so cleaning this up a little bit, 5/4 x to the fourth minus 6 over 3 is 2x cubed plus x plus c is our antiderivative, our integral. In the next example, we're looking at r's. There's no difference there, but the thing that does make this one different is, oops, I have a square root of r and an r in the denominator. We're going to do the same thing we did with derivatives. I'm going to rewrite this integral of a thing. Draw a line there. There we go. dr. All right, so my square root of r, I'm going to write that as a 1/2 exponent. And my r in the denominator, I'm going to write that with a negative exponent. And now I can apply the same rules as the other examples. All right, now you can check this in your calculator if you want to. 1/2 plus 1 is 3/2 over 3/2. And then minus r to the negative. Make sure you add 1. Negative 3 add 1 is negative 2 over negative 2 plus c. All right, so we're going to clean this up. Maybe I'll start with the second term. That becomes minus negative. That becomes plus r to the negative 2 over 2 plus c. You could also write that as 1 over 2r squared. So you could throw the r back into the denominator, but it's not like you don't have to. And then cleaning up this first term, we have a over 3/2 in the denominator. So that we can bring up into the numerator, but we take the reciprocal. And the way that you think about it is dividing by 3/2 is the same as multiplying by 2/3. Okay, so this is 2/3 r to the 3/2. And there is our antiderivative on that one. All right, now, last example, we're given a derivative, given dy over dx equals 3x minus 1. Okay, so we're given the derivative of a function, and I want to find y. How do you find y? You take the antiderivative. But I get this extra bit of information. We're not going to use that just yet. That'll be a second step that we do with this guy, okay? But we're going to have to figure out what we can do with that extra piece of information. The first step, though, is if I have dy over dx equals 3x minus 1, y would equal the integral, the antiderivative of 3x minus 1 with respect to x dx. All right, so I can do that antiderivative. Getting better at these now, hopefully. 3x to the second, add 1 to the exponent, divided by 2, minus the antiderivative of 1 is 1x. It's a constant. Plus c. Okay, so there's a good first step. I've got the equation of my y. It's a parabola. Y equals 3/2 x squared minus x plus c. But how do I use this extra piece of information now? Y passes through that coordinate. Okay, what you can do is, given that additional piece of information, well, now you can find the actual equation, the whole y equation. I can find the c, the constant, because the y coordinate is 4. 4 equals 3/2 times 1 squared minus 1 plus our constant c. Oh, so if I have some more information, I can solve for that constant of integration. And if we simplify this, 4 equals 3/2 times 1 squared is 3/2 minus 1 plus c. 3/2 minus 2/2 is 1/2 plus c. 4 take away a half is 3.5, also known as, what's that, 7/2 equals c. Right, I just did over here 4 minus a half. 8/2 minus 1/2 equals 7/2. Yeah, I got that right. Cool. All right. So that's our constant of integration. So we can now rewrite our y equals equation. Y equals 3/2 x squared minus x plus 7/2. And that's our answer. Cool. All right. That is the end of that section. That's the end of this video. Thank you for watching. Let me know if you have questions. Include a timestamp, and that will make it really clear what you're not certain of. Thank you for listening.